This program is a presentation of UCTV for educational and non-commercial use only.
The final speaker today will be Steve Selkowitz, and he's going to speak about windows as oil wells. And the discussant will be John Mahoney of Chevron Energy Solutions. So let's have Steve Selkowitz come up from Lawrence Berkeley National Laboratory.
Well, thank you. Thank you, Alan. So I want to start by making three comments. One is that so we've got light bulbs and fridges and now windows. I think the windows are going to be a bit different from the sort of product discussions we've had. Obviously, there are themes that are common, but we'll see if there's some differences. Secondly, I've got a quasi-historical spread here, but with lots of deviations forwards and backwards. So just think of it as a movie that jumps forward and jumps backward, and sort of keep the central plot in mind, though. And finally, some of the stuff that goes back 20, 25, 30 years is my recollection of who did what to whom when, and I'm sure that lens is a particular lens, and other people would look at it differently, so it'd be useful to get some feedback in the long run from others who helped move all this stuff forward back at that time. Let's start by the views of windows. And I've got a 1976 view here and a 2007 view, the code official from the past and the architect from the present or the future. These are divergent views, right? I mean, in fact, if you look at the codes written in the 70s, including our good old Title 24, it basically said, windows don't work very well, don't use them, or minimize them, or, you know, those kinds of things. If you pick up a magazine now and look at what architects think are LEED, gold, and platinum buildings, you see an awful lot of glass. So there's a sort of bracketing the world of possibilities. Are windows friends or foes in energy efficiency? Answer is, it depends, I think. So let's look at the performance issues here. And one of my themes will be that in the end, that what we've accomplished with Windows and the trends here depend on the technology, the sort of the first set of bullets there on the physics and the engineering, but also on the second set of bullets, which gets into policy and standards and business and economics. And it's the kind of the interplay between the two that either drives things forward or slows things down. And California's been, I just, at the very bottom here, just say a very interesting test bed, a fertile test bed to kind of play out these things, try them out and see what works and what doesn't. So let me spend a couple of slides here, sort of a primer on where windows fit into the energy picture. So here's the US picture. You all know these numbers. Buildings are 40% of energy and 70% of electricity. The problem with windows, they don't plug into the wall the way a fridge does or a light bulb does. They don't consume energy. They impact energy by virtue of other systems in the building. So on the residential side, they impact heating and cooling, which together are about 42% of energy use. And on the commercial side, you've got heating, cooling, and lighting now, because I'm going to use the daylight from the windows, and that's about 57%. So they potentially impact on the order of half of all the energy used in the buildings, though they don't use energy per se. The other thing that makes this a bit more complicated is the details depend on climate, on building type, on lots of other parameters. So if we go back and do a study, a stock study, and we've got lots of reports on these kinds of things, and say, well, what are the real impacts going on here? We end up concluding roughly that windows consume 4 to 5 quads out of the 40 or so that buildings use. That, by the way, is worth $40 to $50 billion a year, so it's a target worth thinking about going after. And the details between heating and cooling vary, and they vary between residential and commercial. If we drill down a bit and say, what's the potential? How far could we get if we could magically change the world? Here's the commercial sector side of the picture. Current stock uses about 1.3 quads. You know, a variety of improvements there shown as I go down the list. would reduce the levels. And notice in the very bottom there, I go on the other side of the zero line. So here's the zero line. I've reduced the energy down to this point. When I get to a highly insulating dynamic window, I'll explain that a bit later, I've broken into the positive side, and now if I add the daylighting benefits, I've got a couple of quad and a half of extra energy. So if I ask what are the impacts here, I've gone from a cost of about $20 billion a year to a savings of maybe 15. So I've now turned the window into an energy supplier for the commercial sector. What happens on the residential side? Well, this isn't a sector study. This is a single building, just as an example. I start with a building, this happened to be in a heating climate with single glaze with storms, about $1,300 a year bill, and I do various things to it. I get down to, at the very bottom, a super window, $960 a year. Notice just above that, the building with no windows at all is $1,000 a year. So essentially, I'm providing a little bit of extra energy to the building. The building with with super windows is a better energy performer than the windows with the building with no windows at all. So here I've also demonstrated, at least by simulation, that I could change the window from an energy cost into an energy benefit. Okay, so that's the quick story on the background of what the potentials are. Let me do a little bit of history here. Let me remind you that, or just comment that I've been into the zero. This is me in 1961, junior high school science fair, low carbon energy supply. I got it wrong. I got nuclear, but at least I was into the zero carbon nuclear stuff, or zero carbon energy supply as a younger kid. Fast forward a number of years, and I'm going to talk about a few things here. So this is 1976, and that's me in the upper right with a lot of hair and hair down to my shoulders and a long beard and all that. Look at the second image there. This is can't maybe see it that well. It's a beach ball. It's the world running out of oil. 1976, right? The world was running out of oil. It was a crisis. We've heard that recently. I was teaching at that point. I taught in an architecture school. I had a consulting business too. I'll talk about in a second. And the last project I did at that place was this report, 100-page report on how you would produce a zero-energy community north of Los Angeles. And we did a pretty decent job. This wasn't just energy. Energy was almost the easy part. We used wind, not solar, because solar didn't make any sense at that point. Solar thermal did, PV didn't. But we did water recycling, waste. We grew our own, the design was grow your own food. We redesigned appliances, by the way. I've got a refrigerator I need to show David at some point that did some very interesting things. But the other important thing, we had this little digital meter in the kitchen telling people how much they were using. Google discovered that a few weeks ago, right? They're going to put meters in people's houses to show them what to use. It's a great idea. These ideas aren't exactly novel. But what was interesting to me, so I had a consulting job at the same time, and we did solar studies. And mainly they were feasibility studies, because when we did the studies, we basically proved it didn't make sense to do them. This was in the 70s. Energy was cheap. It was unsubsidized. But in 75, we started getting clients who came and said, help us to analyze the energy performance of buildings. And these were people who were building houses in the Malibu area on the coast, beautiful west-facing views over the ocean, and they wanted to build the house they've always built, which is lots of glass. And they ran into something called an energy code that was newly enforced at that, or newly on the books anyway. Whether it was enforced or not wasn't clear. And they needed to show that their beautiful house on the beach was going to, well, they couldn't meet the prescriptive part. I mean, they just, with all that glass, it just wasn't going to do it. So they needed to show that their house used less energy than a house that met the code. So we got into the business of trying to understand how these houses would really work, which got us into looking at, well, how does this energy stuff really work with respect to windows? And we also sort of fitted them up with the best available appliances and with solar water heaters and everything else you could do. In parallel with that, 1974, I believe, the physicists, the APS, did a study on energy efficiency, and it concluded, not surprisingly, this is some of the precursors of stuff that David showed too, that there was lots of savings to be had. Now, the physicists came at it from their point of view. There wasn't much there on the market side, but the potentials were clearly very, very large. In 75, Art Rosenfeld and others organized a seminar, actually a 2 or 3 week summer study in Berkeley, where a lot of people came together and talked about these issues. And the physics and the engineering got blended in with the markets. And out of that came an invitation from the Department of Energy that said, gee, this stuff sounds interesting, write some proposals and maybe we'll fund them. And Art and Sam Berman at the time said to me, well, you seem to have fit in well here. I was still teaching and consulting in Southern California. Help us write a proposal or two. If it gets funded, then move up to Berkeley. And to make a long story short, 33 years later, I'm still in Berkeley. So the origins of this were kind of interesting. Let me go back for a second to then the vision. And one of the things we did was we looked at windows. That was one of the first things that we looked at. And that's because those physics studies had said there's some opportunity there. So we tried to define the vision. And the vision here again is converting energy from losers, net losers, which they were and still are in a big way, to suppliers. And the issues of what you need to do with heating and cooling and daylighting are kind of outlined here. We went further and developed some research plans for DOE back in the mid-70s that looked at highly insulating windows, that looked at dynamic windows, daylight. And in the first two areas, we've made in the last 30 years real serious progress. The last two, not quite as much, but I'll get into this in a bit more detail. So what I'm going to do is start with the insulating window area, which was the focus of the initial work and where in some sense the world really has changed in a substantial way. So if you look at the problem of, well, I won't even talk about single glazing, but a double glazed window, you look at the heat transfer pass, and you discover that if you want to do something to modify a double glazed window, the thing to do is to reduce the radiative loss across the window. And for that, you want a transparent LowE coating, low emissivity coating, which is shown. We put in place a program, and I'm going to spend a few slides here sort of talking about the details of that program, to try to invent the technology, the coating part of it, get the window guys to put it in their window systems, because they're different. Window people are different than glass people, and then get people to think about it and buy it and so on. And this is just a very short way of saying we're sort of talking about what we've been doing for the last 10 or 15 or 20 years. There are a lot of different issues here. Some of these are shown here. Coating design, the thermal performance optimization, how do you make it? Is it durable? What does it cost? And so on and so forth. Lots and lots of different issues that had to be confronted. When DOE asked us to get involved here, they said, we want to fund some folks in the private sector. Would you help manage them? And there was this clever group called Suntech that was back at MIT, and they had some clever ideas for a LowE coating. But although they were a company developing coatings, I just pulled out a page here showing that, and I realize you can't see the details, but this is the market structure for how you get from flat glass to the consumer. And it's pretty complicated, lots of different pathways. In fact, their proposal to DOE was a retrofit product, and after a year's worth of work in understanding all this, they end up saying that's not the way to go, at least at the beginning. They went for new window construction. And again, I'm sorry, I realize you can't see these, but this is our first report, Sam Berman and I's first report to the Department of Energy in 1978, saying, what have we done with your money for the last year? We did a few useful things. And on the right, actually, a monthly magazine at the time, 1978, it says, window heat mirror films move toward marketplace, only a year or so after the research was funded. And it actually, I read it through last night, it quotes me, and actually the stuff I said wasn't too bad. It said that this looks promising, but there's work to do. And that was pretty much the way it was. Skipping ahead, 1988, 10 years later, so these products were introduced in the market in the early 1980s. Interestingly, the company there, Suntech, which became Southwall, is still in business, makes great products, never captured much of a market share because their strategy was to put the coating on plastic, and that makes things a little more complicated than putting on the glass. In the meantime, though, other firms, big window companies and suppliers, saw the opportunity, in part stimulated, I believe, by the funding to this small group, and pushed forward on their own. And so the product was available fairly widely by the early 80s. 1988, though, we published this report, which is High-Tech Window Coatings Supply Energy Services. So this is back to the theme. And I did a calculation that if you built a sputtering machine is the machine that coats the glass, and you figured out how much glass it makes over 10 years and how much energy that glass saves over the lifetime of the glass, it was as much as a $300 million 10-well oil platform off the coast of California at the time, roughly equal in energy units. So this theme of demand and supply being equated was one that we were talking about back in the 80s. Now, skipping ahead a bit, 2000 administrations change. People are less clear that energy efficiency makes sense. DOE commissioned a report through the National Academy energy research at DOE, was it worth it? And they looked at about 20 or 30 different things that DOE funded. Some of them were failures. Research sometimes fail. One of the things they looked at was LowE Coatings, and this is a pretty nice report. It talks about what we did, it talks about the issues. The conclusion was that for a DOE R&D investment of about $10 million, the country had a net savings of about $8 billion. Now you can argue with the details, but if you look at the decimal places, that's pretty impressive. So there's been some progress and some history here that's been quite interesting. Okay, now there's many other types of coatings out there. So the good news is we got LowE coatings in the market. Remember I said at the beginning, you don't have a one-size-fits-all here, so we have to worry about which coatings work best where. The products that we targeted at the beginning were cold climate products. You say, well, what works in California? You have cooling issues. And so, in fact, there are different flavors of coatings, some that work best in the Sun Belt, some that work best in the North. And this has to do with the properties, a little bit of techie stuff here, the solar heat gain coefficient, 0.39, 0.71. So these both let through the same amount of light. This has half the cooling load of this one. They're both variants on LowE coatings. So there's a little bit of a problem there of how do I tell them apart? How do I figure out what to use? If I'm a window guy, do I make both? Do I make one? Some challenge. The other challenge is what I'd call the emperor's clothes problem. I can look at 4 windows from double glazing with nothing to triple or quad glazing with LowE, and if I look at the glass, I can't tell what's what. I can't infer performance from simply looking at it. This is an IR image of that, and I can tell from an IR image. So if we equipped everyone with a $25,000 IR imager, you could look at windows and you could tell which are the leaky ones, this one here, and which are the really good ones here. These are warm on the inside, which they should be. But the challenge for the consumer is how do you figure that out? And so what we did was we said, we need to rate these things and label them in much the same way that you put a label on a fridge that says what it does without having to dig in and look at all the internal components. So we got a group going, the National Fenestration Rating Council, about 15 years ago. That group started looking at how would you rate windows, how would you do it in an objective, neutral way, accurate way, but make it feasible and cost-effective. And it made some progress, but not a lot. But California came along and said, look, we want a window rating process. We want it by, whatever it was, 6 months from now. If you guys in the NFRC don't do it as an industry, we're going to do it ourselves. And that scared the industry enough to sort of get their act together and actually put the first program together and launch it. California now mandates if you sell a window in the state, it must have an NFRC label. These are pretty widely used throughout the country. Now, this rating and labeling process has a pretty good technical underpinning. We developed the tools for NFRC so a manufacturer could rate and label a window at low cost. The way they used to do it was to send everything off to a test lab. It's a very expensive way to do it. So there's a technical underpinnings behind this, a set of research facilities at the lab that basically back all this stuff up and convince everyone that the numbers are right. So these ratings and labels are now incorporated into building codes and standards. I think this is just a picture of the different standards in different parts of the country. I believe 37 states reference the NFRC labeling procedure. So if we look now at progress, what kind of progress have we made? Going from 73 to 2008, about 35 years, we've gone from a world of largely single glazing to 95% double glaze, 60% LowE. So this is something that didn't exist when I moved to Berkeley, and actually at this point, 30 years later, it dominates the market, so much so that the Energy Star rating, which basically to first order means having LowE, needs to be updated because it's no longer distinguished from the marketplace. But now we're looking ahead to 2020 and net zero windows, and what do windows need to be in the future in order to go even further. And so one of the challenges is these highly insulating windows. Here's a couple of concept designs of what you would want or need. Multiple layer. On the left, these are things you can do today. Plastics, glasses, gases, coatings, off-the-shelf combinations. On the right, an evacuated window and an aerogel window. These are more in the research realm. So there's lots of opportunities. The problem is the market isn't moving there, because if you ask the manufacturers, they say the market doesn't want them, the market isn't demanding them. Another interesting way to look at this, here's a kind of, again, concept diagram of time on the bottom, going from single to double to LowE. And we're in here somewhere, the late 2000s. And so we've got these R3 and maybe R3 windows in here. We want to get to this R5 or 6 range. At that range, a window shifts from being a net loss in most of the country to a net gain. And that probably means going to a triple type, or one of the things I just showed you in the last slide. I'm calling this a market force field. The market is pushing back, or at least it's not accepting it. So we're doing a variety of activities now. Some examples here: building prototypes. DOE is funding some companies to build cheaper R5 windows. We've put them in test houses to measure and demonstrate them. We did that in the 80s, by the way. We built a house in Montana and showed that a north-facing window was a net energy gainer when it was 20 below zero or something. So it's not that it hadn't been done before and someone hadn't written a report about it. You still have to push a lot harder in the marketplace to make this stuff work. And then DOE is considering a volume purchase program for high-R windows. And interesting concept, it's been done before in other areas like light bulbs. Whether it makes sense or works here or not remains to be seen. So let me switch a bit and talk about the cooling load side, which is certainly more appropriate for where we are now and for much of the country. Glass and solar control, lots of opportunities here, lots of issues. The first comment to make is that LowE does a pretty good job here. These are the variant of the types of coatings I showed you before, showing that here's the visible part. They all transmit a lot of light in the visible, but depending on what they do in the near infrared, you can get windows that are more efficient than even a 200 lumen per watt light bulb in terms of the light transmitted per unit solar gain. This is an interesting plot of all the glass sold in the US, 2,000 types of glass, plotting them against the solar heat gain coefficient, which is, again, is the cooling part, and the visible transmission part, which is how much light comes through. The good news is there's lots of opportunities. The bad news is, if you will, if you're an architect or a homeowner, what do you pick? I mean, is this better than that, or is that, I mean, it's confusing, right? So one of the issues, and one of the reasons it's important, this is particularly important on the on the commercial side because of the daylighting world. So I want to say a word or two about daylighting. Remember, lighting is the biggest consumer in the commercial sector, so we want to effectively use windows in that sector. This is a systems problem. Again, it's not so much a glass properties problem, it's a systems problem. It's a bit complicated. Daylight penetration has not been what it should be, but going back again, examples, 1990, Emeryville, so California demonstration project, measured this is the days of the year, measured the lighting energy use in the building across the year in the pre-retrofit, pretty much constant, retrofit dimmable lighting controls, and on the south side of the building, we got 40 to 60% savings. On the north side of the building, got 40 to 80%. Now people say, well, wait a minute, shouldn't you get more savings on the south side? There's more light there. What happens on the south side? There's too much light, too much glare. People close the blinds and the shades, and they don't open them again. We're not perfect shade operators. So this triggered us again to this intersection between shading and glare and energy and comfort and the properties of what you might want to develop and use. So the challenge in the daylighting world then is kind of solving this systems problem, and I could spend a half an hour talking about this, which I won't. It's an integrated problem. It's a heating, cooling, lighting envelope problem. You need to worry about the electric lighting controls part of it, but you need to deal not just with the engineering, but the comfort and satisfaction as well. And in many cases, you're going to need tools to let people do this analysis and optimization. And then finally, you've got to get the design right, but you've got to think ahead to the operations, because if the sensors don't work right, if people aren't comfortable with what's going on, it's not going to work. So this gets us into this issue of, well, what's the right kind of glass to use? And we get asked this question all the time, and unfortunately the answer is it depends. Again, it varies with all these parameters. So a logical response is, well, let's just get a glass that does everything. Why not have a glass that changes from clear to absorbing in this case? Now, this is ongoing work now, but one of the proposals that Suntech was funded for in 1976 was a glass that changed properties. That one didn't go very far at the time, but the point is it's not a new concept. And it turns out the good news is, again, there's lots of options for doing this: heat sensitive, light sensitive, electrically controlled coatings. And each of them has their pros and cons. We tend to favor the electrically controlled approach with active control because thinking about the way you want to control heating, cooling, and lighting a building, I want to be able to control it when I need it. I think those are motorized shades up there. I'm guessing they might be on the middle level, and you'd like to be able to open them and close them when the use of the space is appropriate. I presume they're closed now because we're showing slides here, and if we weren't, maybe they'd be open. Don't know, though. That's just a guess. But that argues for having a a dynamic system. Now, in terms of the work that we've done in this area, this is a systems problem again. So this shows, this slide got scrambled a little bit, but everything from the material science to manufacturing to savings assessments to human factors work to test beds, all of which is needed if you're going to move this technology into the real world. So one of the things we did, we looked for people who were interested in testing this stuff back in the 1990s, early prototypes. We found them in California. So this is Oakland. PG&E, this is a GSA building. PG&E funded the work. We tested out in the Twin Towers in downtown Oakland. This is a view inside. We looked at color and glare and privacy and switching speed, all the things that would sort of help you get this from a prototype to a real product. It moved the benchmark forward a bit, but not enough. We subsequently built a facility at the lab. This is the only one of its kind in the country. 3 side-by-side test rooms. These are prototype electrochromics from 5 years ago with a base case on the right-hand side. They're heavily instrumented to do the engineering work, but we also put people inside, and we asked people, what do you think about this? Do you like it? Is the blue color displeasing? Does it switch fast enough? So once again, if you're looking at something that's going to impact the market, you need to understand the human factors issues as well as the technology issues. And then there's the business issues, and this is interesting. This is a group at the Haas Business School in Berkeley, clean tech to market, C to M. So the VC world and the clean tech folks have rediscovered efficiency, which is great. And this student project was sort of said, well, let's look at why these electrochromics aren't making it to the market, what's needed. And so they went and built their own model of what the marketplace looked like, much like Suntech did 25 or 30 years before that, which is interesting. So let me close this section by talking about a few sort of systems issues. If we're going to get advanced windows into the world, we need to think about systems. So here's the systems concept. There's the envelope stuff, and it relates back to what you do with lighting, HVAC, a utility meter that may have a real-time price signal or at least time-dependent costs. And I think John is going to talk about some of this in the real world when he goes to retrofit a building. Once again, California leaders, this is a building, it's another GSA building, downtown San Francisco. This building on 12 floors has no mechanical cooling. It works, it's cooled in the summer by having windows that open, the cool San Francisco breeze blows through, there's exposed concrete ceilings, lots of other design details cleverly worked out by the architect and engineer so you could do a non-cooled building that will meet the comfort requirements. So doing these things, first off, these are risks involved. They're interesting, again, in moving the benchmark forward here. Why is this important? This is a load shape showing that in a typical California peak load, about half of the load on a hot summer day is cooling and lighting, other loads here in the bottom. And if I aggressively pursue the window control and the daylight control, I can cut down about 20 to 30% of that. So there's big savings potentially there. So this concept now is using a smart controller to control the conditions of the window, to control the daylight, and to be able to do it under this range of input conditions from what people want and need to what the utility is telling you to weather and so on. So this gets us into the systems world again, which makes this problem more complex. So I'm still looking at windows, but I've got to solve the window problem in a lot bigger context. This is the cost side of that. So if I'm going to put all of that extra stuff in there, those controls, I'm going to add some cost to the building. My point here is normally we do the cost analysis in the box on the left. I increase the cost of the window, I save a little bit in heating, cooling, and lighting. I have a first cost and annual savings, I divide the two, and I get a payback. And John will tell you, I think if the payback is less than X years, you'll do it, and X is a very small number. It's a single-digit number, and it's a small single-digit number, but I won't steal his thunder. But what I'm arguing is, let's look at the big picture. Let's look at the impact of these windows on chiller size. I can maybe save some money here. If I can downsize the chiller, I can put it into the window. So I'm a friend of the window and shading and daylighting guys. They like me. The chiller guys don't like me quite as much because I'm arguing for shifting the balance here a bit. Now, can we convince anyone that any of this stuff makes sense? So here's a real-world project. We were approached. This is the New York Times new headquarters building. We were approached by them 3 years ago. They said, we've got this great new building, an all-glass building that's being built. It has great daylight potential, but we want to make sure we capture the savings. We want to make sure that people can see their computer screens in a building that's all glass. Can you help us? They'd seen some of those studies I showed you before. I said, well, it's great. We've done this. We know we can do it in one room. The question is, can you do it in a 1.5 million square foot building? And just because you can do it in the first doesn't mean you can do it in the second. We convinced them that this was a complex enough problem that what they should do is build a mock-up, a full-size mock-up, 5,000 square foot mock-up of a corner of the floor plate. This is what one of the floors looked like. And this corner, 5,000 square foot piece, was built in New York, a few miles from the site, fully furnished with multiple systems, multiple shading systems. The issue here was motorized shading, because we told them electrochromics weren't ready for the market, and multiple types of dimmable lighting. Lots of instrumentation, full year's worth of measurement. Now, the trick here, and we'll pat ourselves on the back a little bit, wasn't to pick the winner and install it. It was to develop a spec, a performance spec for this, which was then bid back out into the marketplace. And that generated a lot of interest in the market. A number of manufacturers responded to it, and the Times then got the option of putting together a really good package. This is the inside of the mock-up, showing all the different systems being used here: underfloor air, special furniture systems, the digital lighting controls, and so on. And arguing here, this is sort of the package, the win-win package here, that this mock-up served a number of different interesting goals. One of the things that happened while the mock-up was up was 400 architects, engineers, and owners from the New York area toured through it and got to see what the potentials were, and a lot of those came back later and said, that's something we want as well. Now, that's exactly what we wanted. We wanted the signal from hundreds of architects and engineers to go, not to us or DOE, but to go to the manufacturers to say, improve your shading systems, improve your lighting systems. These are viable in the marketplace. If you can make it, they will come. And to some small extent, that's what's happened. So here's the building. It's finished. It's occupied. Seems to be working pretty well. Largest installation of daylight controls and automated shading in the world, we believe. We hope to be able to get into that building next year and do a study to find out what the measured savings are. In the meantime, the cost for dimming ballast, which is a critical issue, came down from about $100 a ballast, roughly, a range, to about $50 in this project. We have a target of around 20 or 25, and just this week, a group was convened at CLTC with Edison and some of our folks and others to look at the dimming ballast issue and can that be put into the Title 24, 2011, or 2014 standards. So you can't put things into standards if you first can't show that it's viable and makes sense in the real world. And the purpose of a project like this is to, in fact, do that. Now, one more New York thing before I close back on the West Coast. If you read the paper last week, you will have seen lots of press. The Empire State Building is doing a massive retrofit, 38% savings, I believe. Down here, you can't quite see it. Triple glazed insulation on 6,500 thermal pane windows using existing glass and sashes with a plastic film. That's the plastic film that came out of Southwall. Or that will come out of Southwall. So here's, you see where we are here. So it turns out they've been a player here. The company that makes the LowE coating on glass, or actually the machines that make LowE coating on glass, is currently Applied Materials, which is located here. It had 5 names in the last 20 years. It got bought and resold and moved, and it's been in Berkeley and it's Fairfield. It's in Fairfield now, and another partner company was in Santa Rosa. So there's a lot of California-based innovation and manufacturing going on. These machines, by the way, are sold in China and Asia to make coatings over there as well. So we're not just helping save energy in the U.S., we're helping to save energy overseas as well. So back to the California link here as well. So finally, how do we wrap all this up? These poor architects and engineers I referred to a few times, if they're going to do this optimization, they're going to need better tools. We produce, and others as well, a lot of this is with DOE and CEC funding, a series of guides and books, a series of websites. This is a website you can go in for 250 cities in the US, including all the California climate zones, get a list of 30 or 40 windows on the residential side and find out what the energy performance of each of them is. Tools that can be used by architects and engineers on the bottom here to do the optimization, energy tools, but tools that can be used by the manufacturers here, this tool called Window, in fact. It's too bad it's not the other window, the MS window. But window, which lets you put in glass and frames and tells you what the thermal performance is, tells you whether it'll meet a Title 24 requirement, and it helps the manufacturer do virtual design or redesign if their current product won't meet the old one. The way they used to do it was build a prototype, send it to a test lab, expensive, consuming process to innovate. Now they can do it with a simulation tool in hours rather than weeks, and this feeds into the NFRC ratings. Websites that give you, this is now for architects, you can put in, this is for the commercial building side, put in your building, look at the glazing options, look at the shading options, look at the daylighting options, and get a pretty quick answer: energy, peak, carbon, comfort, amenity, all those things. And this is for standard stuff. There are other tools that let you do this on your specific building. So concluding, there's a pathway here towards this goal of net zero energy windows, or high performance windows for net zero energy buildings. We've talked about the material science, the engineering, the physics side, but also talked about the human factors issues, the fact that we need to look at systems, not individual components, and we need to look at this sort of life cycle integration theme. It's interesting that in California with the PUC and nationally, AIA and others are all targeting the net zero as a goal, which is great. I think we aren't going to get there as quickly as some people think we are, but you need to have those aggressive goals in order to do all the intermediate steps that David talked about before as well. My recipe for how to get there: vision, passion, perseverance. I tried to do all P's, but I ran out of luck. But being humble and lucky probably doesn't hurt either in the bottom there. But I want to stress here that the things I've talked about very quickly today, lots of people around the country, public, private, industry, academia, labs, and others have been involved. And frankly, at least from our point of view and many others, this wouldn't have happened without the continued support, little bumps at times, from DOE and CEC and others. The public sector has been the entities that have kept all this going when the private sector decided it wasn't worthwhile or it wasn't cost effective. And you don't hire and fire people on a yearly basis if you want to make this stuff work over time. We always ask the market what it wants, and that's important, but I want to put in a little caution there, a quote from Henry Ford. If I'd asked people what they wanted, they would have said faster horses. You ask people if they want R5 dynamic windows, they don't tell you they do because they don't know they're possible. So we should be a little careful. We always talk to the market, but then we look at the market from the public side and the societal side as well. Sometimes you get different answers. Finally, where does all this R&D and innovation fit in? Obviously, the techie part, the new and improved options is important, but this is not just the technologies, but tools, business processes, and models. And I'm going to argue from projects like the New York Times that aren't one of the biggest things that R&D does. It reduces risk and uncertainty, reduces the time in many cases, and the cost, which in the business world is worth as much or more than performance. You've all seen versions of this slide of how you move markets forward, that R&D pushes the right-hand end to the utmost efficiency, various types of subsidies and ratings and labels and marks and standards that cut off the bottom. So this is conceptually still the model we're using. The mix of what you do, though, is going to vary with the problem that you happen to be tackling. So the last summary, this is the old win-win-win here, that we can do the right thing for people. And I want to bring people back into this, especially with Windows. You've got to do the energy thing right in the middle here, and the owners need to see the added value and the benefit, but you've got to do something that works for people as well. Otherwise, they'll never make the investments that you want them to make. And if we do these two as aggressively as we need to, we're going to end up helping solve the climate change carbon problem as well. Thanks very much.
Thank you, Steve. John, it's your turn to comment upon it, and I hope from a practical standpoint, I saw you smiling a couple times too.
Let me start by saying that we love to do windows, and we think they're great retrofits. Unlike other energy efficiency measures that we do, they're one of the few that the customers can actually physically see. They can physically touch them. So much of what we do when we do an energy efficiency project is behind the door, in the mechanical rooms. It's down in the basement. It's up in the roof. So the customer never really sees the actual improvements that are being done in the building to make it more efficient, to make it more green. In fact, that's one of the reasons why we typically put solar out in the parking lot rather than on the roof, because we want our customers to see it. And and that's what we love about Windows, is that our customers can see it and they can touch it. But it's not easy because despite all the existing improvements and potential breakthroughs, they're generally a 15-year or longer payback, and in some cases 20 and 25 years. So if we do a window energy retrofit, and we do it on trying to pay for it from savings, generally we have to incorporate other type of energy efficiency projects or components with it, like lighting, controls, electrical, mechanical retrofits. And so we're trying to make it more economically feasible for the customer to get new windows. Because believe me, I mean, our market that we serve, our primary market is the public sector. So if you can go into a 50-year-old school or an old campus and you can tell the facility director or the superintendent that as part of this project you're going to be able to replace their windows, they get very excited about that because they know their faculty, their teachers, their students will see that as a visible improvement. And so, they love it when we can do it. It's just not easy to do. From a practical standpoint, when we do full window replacements, generally it's in conjunction with a modernization. It's an energy efficiency project that's been married with a modernization type of project in a school or a municipality or a college. But that's obviously when it makes most financial sense because you're going to expend the labor anyhow to replace that window. So all you have is the marginal costs associated with making it more efficient. So we always look for those kind of opportunities to be able to blend energy efficiency with modernization. The other part of window, and I'll call it window systems that we look at, that Steve mentioned, was to try and integrate shading, film, and integrate that with our controls. And typically when we do an energy efficiency project, it almost always includes some sort of control enhancement, building automation improvements. And it really, again, you just have the marginal costs associated with taking that large shade there and automating it and somehow tying it back through a sensor to be able to know when it should be open and when it should be closed. And so we do a lot of that when we're talking about windows. Now again, that's not a full window replacement, that's just a way of making and improving the comfort within the building and using that technology to do it. We've done a lot of projects with windows. There's some projects where we're actually kind of looking at it from maybe I should step back for a second. We try and go in and we try and do a holistic approach when we look at a building. We try and look at, we look at the entire consumption of energy within the facility, where the BTUs are being consumed, where the saving opportunities are. And so we're trying to see if we do replace the windows, what kind of impact is that going to have on the HVAC? And if we do windows and lighting, can we really downsize the size of the chiller, as Steve mentioned? And that can have a nice financial payback or make the windows more cost effective when we do that modeling. That modeling is expensive, it's also very time consuming. But it's the right thing to do if you want to really get at most of the savings within that building. We've also, so it's interesting, some of the projects that we've done with windows include when we go into an old school, for example, we'll actually yank the whole wall of the classroom out and we'll put a whole new wall in. And in that wall will be a new air conditioning unit, a new energy efficient air conditioning unit, and a new window, and maybe more insulation in the building in the side of the wall. So you go into a school that was built 50 years ago, and it has like a very small amount of mortar on the side of the wall, and most of the windows are ugly, they're leaking, and so we take them out and we put a whole new wall in. I already mentioned the fact that we do a lot of film. For example, St. Mary's College in California, we replaced we added film tinting in order to improve the heat load in the dorms, to be able to make the dorms more comfortable. So that's just kind of a feel for some of the projects we do with windows, and I was telling Steve this earlier, is that our customers love it when we can do windows. We need to find a way to make them more cost effective, We need to take a look at the whole system of windows, the fact of how they're made, how they're produced, the incentives that are provided. There are very few incentives for windows, really. On the commercial side, there's a deduction. It's the IRS 179D. It gives you, I think, 60 cents a square foot. I think that's 60 cents a square foot, roughly. And you have to be 50% more efficient than the ASHRAE standard. It's and you have to do a lot of measurement to get the tax deduction. So we do go after it when we do the work, but generally speaking, it's not something that a building owner would encourage a building owner to make that long-term investment. So we have to find additional incentives. We have to find more cost-effective windows. We also have to look at the labor content. One of the projects Steve was showing was the Empire State Building. Unfortunately, that was done by one of my competitors, so I don't want to brag about it too much. But basically, they set up a refurbishing shop right in the Empire State Building. And so everything was done right there on location. It was more cost effective. All the supplies were taken there, and all the refurbishing was done right there on site. So those are the kind of things that you really have to start thinking about, is how can we look at this whole window replacement as a system as opposed to just an individual event. So we would love to do more windows, but they just need to be more cost effective. So.
Thank you. There's a question.
Good afternoon, Mike Amon, Solano EDC. I work with a lot of groups like Coronet, who are both owners and users of buildings, and we're just starting to see some data that actually promotes the idea of investment. The LEED standards, you get higher lease rates, you get happier workers and some of this, but it's still very early on. And I don't see anything out there that really promotes that. I can, even in the last couple years, we've started to see the chief financial officer start to pay attention to some savings versus a tenant who just wants the cheapest space possible because I'm never going to be there 20 years to get the savings. So is there any discussion out there to help move these standards along so that we can convince not necessarily the person who's in the room with the windows, but the CFO, the one who will sign your check?
I would say, first of all, I do believe that there are benefits of that sort, both for the people and ultimately then for the CFO. Being able to quantify them and and here's the really tricky part, being able to attribute them to something that you do. In other words, let's say hypothetically a green building is worth more, whatever. No two green buildings were alike, so what is it about that building that made it work better? Was it the green roof? Was it the windows? Was it the light? Was it the carpet? Was it the VOCs? No one knows that. So my first comment is I truly believe these benefits are there. I'm rather skeptical of most of the data that I've seen to date, and I think more work needs to be done to get it to the point where I can tell a designer, if you do X, the consequences will be Y. I think we can get there to varying degrees in certain areas. There are also some flawed studies out there. There are some studies that make all kinds of claims that other people have refuted. And so I would urge caution but optimism, I guess, is the way I would put that. And be happy to chat afterwards about details of at least what I know. But I think that would go a huge step towards moving the market if the people that make the decisions, or the people that John deals with, believed all that, and it was real as well.
Well, I think you're right. I think there's a tremendous movement towards looking at sustainability as part of the financial equation. Whether you're in a commercial building or public sector building, and or whether you're a tenant even. So you're concerned about those things, and there are standards, obviously, from the Green Building Council. But I think, to Steve's point, I think there's a lot of room for improvement in terms of making the financial case for sustainability. We've had a number of meetings with an architectural firm, HOK, who you may have heard of, one of the larger architectural firms in the world. And they really, they believe, they truly believe that sustainability And making a green building should not cost more than a non-green building. And so, and we have to start thinking about it from a retrofit and from being able to go back and retrofit these buildings as well to address the concerns of the CFOs and the people who have a financial concern. I know there's also a lot of work, and I don't know, Steve, you may want to comment on this, about the green lease, GSA green lease and things like that, where people are also, we're trying to, put together the structure, the contractual structure that would encourage tenants to make improvements in their space as well. So.
And actually, California, again, is sort of out in front here. I think AB 1109, which requires a disclosure of actual energy performance at lease or sale, is a step in the right direction. In Europe, all buildings must be labeled and rated like that, and both from what's called an asset rating of what the building is capable of, if you will, and an operational rating, which is what it's actually doing, and the two may not be the same because there's a distinction there. So if you don't know, if you don't know how it's actually working, then you don't know what you're dealing with. So I think getting to the point where these things are disclosed and rated, I think USGBC ratings are moving from the hypothetical as a design rating to more of actual measured data. ASHRAE is getting into this world. California is going to require it, which will push everyone forward. So I think you're seeing a bunch of converging forces here, which will move us in the direction of at least disclosing the things that can and should be measured. Some of the other things you brought up are a little bit trickier, but if we can't get the basic, how many dollars per square foot, kilowatt hours per square foot, then we don't even have a starting point.
I spoke to the building manager at the University of California, Davis, and asked him what he was going to do with the stimulus funding, and he said, windows. There's just no question about it. He said they were easy to roll out. They were the number of windows was easily adjustable depending on how much money he would get, since he didn't know whether it was going to be zero or a lot. And in addition, he said that there were obvious benefits to the occupants from doing these retrofits, especially if he focused on the buildings built between, I think, 1970 and 1990,
yes, right.
which were these particularly poorly built with respect to windows, and so he knew his target, and he was just waiting for the money to come, I guess. So I think you've got a market there. You might want to make a telephone call. I got one question that arose earlier. Actually, if you have any comments on that, because I'm going to change the subject.
No, it's interesting you should say that. Some of the conversations we've been having with HOK center around trying to address sustainability and just that set of buildings you were talking about with major campuses and universities and colleges around the country, particularly community colleges. There's a huge amount of construction in community colleges in the 70s and 80s and the 90s, and they weren't typically of the best construction. They didn't get the dollars from the donors to match the public funds. So they're not very good buildings, and they have a lot of needs. I mean, they have a lot of moisture problems. They have a lot of decaying building envelope and window problems. And so, we think that's a great market opportunity for us, and we've been pursuing that very aggressively. And we're working with not just HOK, but a lot of different architectural firms across the country trying to address that issue.
Steve, did you have a point on that?
No, I think there's a lot of interest, and I think that there are issues of things like lead times and the pragmatic problems, but I think you sort of couched it that actually I hadn't thought of that before, that you can do 20 windows or 200 or 2,000 depending on how much money you get. So that's a clever approach. It's not like a roof where pretty much you get how they do the roof or not. So interesting.
Another question. What work has been done to identify non-energy benefits and value streams related to high-performance windows?
Well, okay, on the thermal comfort side, that's something that's moderately well quantified in the sense that one knows that a cold window will have certain, or a hot window will have certain thermal comfort issues. There are some studies that correlate thermal comfort with productivity in different ways, although not at the level of separating out the window. There's been some good work done in the daylighting area as well. But again, I think the problem is that the best we can do is we can say at some high generalized level that there are correlates between a building that's daylighted and satisfaction and people. But when you get down to, if I make the window 30% bigger or I change the glass from A to B, does that improve or disprove or increase or decrease productivity? We aren't there yet. One of the studies we did with the New York Times, that was an automated shading system, and we had to come up with an algorithm that raised and lowered the shades. And the question is, at what point in brightness? So you've got the shades up and you've got the window, and at what point do you close the shades? Well, you need to know how people respond, both from a performance point of view, can you see your visual task, but also is it too bright from a glare point of view? And we did studies in those test rooms and came up with an algorithm, and that's the algorithm that's implemented in the Times building at the moment. One of the clever things the Times project does, and this is from the vendor of the shades, is there's a touch screen beside each 5 windows. And if you're in the space and you don't like the way the automated system works, you can go to the touch screen and you can call it up and you can change where the shades are. And when you do that, it records the change, it records the outside and inside conditions at that time, and it even gives you a little screen that says why you're doing this. You don't type stuff in, but it's, too bright, too dark, I'm hungry, whatever, and you check off the box. And so it's going to build a database of how people responded. In principle, over time, we could gather data from that and then change the set point. On the dimmable lights, by the way, the lighting is a big issue. One of the points of putting dimmable lights in, we push them because they save energy for daylight. But in the end, we recommended they do them in the entire building, even where there wasn't much daylight. Why? Because people like different levels, and we don't exactly know how much different people like for different tasks. So what they've done in that building is they've got the capability of doing 500 lux everywhere, but throughout the building on even a desk-by-desk basis, let alone zone-by-zone basis, they can retune that just simply sitting at a desk, no wiring, no electricians, no switches. And apparently, most of the building has been adjusted so that the nominal light level needs meet the requirements, or at least the desires put forward by the people in that space at that time, and it can be changed. So if I leave the space and you move in and you want the light twice as high, then you can get that too. Now, correlating all that back to productivity, it certainly correlates to satisfaction. Whether satisfaction correlates to productivity is something that's unknown. Well, it's not unknown, it's plausible, but again, the details of it aren't known.
Are there any other questions? Here's one more. Can windows and solar photovoltaics be integrated as an energy-producing fenestration without significantly sacrificing optical qualities? And I guess I'll add to it, and do you think you can sell that?
Well, the second one's easy, right?
Yeah.
John was talking about how important cost was, and at the moment you'd be hard-pressed to sell that because of the cost issues. But here's the problem with PV, and I'm a fan, so let me start with that. There are two problems. One is you've got something that's pretty expensive, and you want to optimize power out for dollars in. And where do you put a PV system to optimize that ratio? You put it on the roof, more or less horizontal, more or less tilted, not too far up from horizontal. That's not where most windows are. Most windows are on the vertical side of buildings. So at best, on the south side of a building, you might do okay. On average, a rule of thumb I use, and pretty crude rule of thumb, is you degrade the performance of PV by a factor of 2 by putting it on the vertical side of the building. Now, there are some other ways around that. You could put a sunshade that hangs out at 45 degrees off the building. Now it looks like a roof, so you can be clever. So that's point number one. Point number two, there is technology where the PV is in the glass itself. And so a roof dome like this for a bunch of buildings in Europe where the glazed roof has the PV in it. And then the PV acts as a diffuser and rejector of sunlight, because if you've got all this glass, it's too bright anyway. So that it might work in an atrium roof or a roof like this to some extent. My view on a window is you're going to sacrifice visual quality, that if you want to, again, squeeze the most performance out of this expensive piece of glass, Then you want to get, it's going to be dark because you're going to want the PV to work as effectively as possible. So I see, I'll just call it a challenge at the moment to come up with that optimization. I'd say the best bet would be a sunshade type device or an application where you want to diffuse and reflect light anyway.
Okay.
John, did you want to add to that?
No,
Have you done any projects that?
No, not really. We've been talking to technology companies that are looking at that, and you know, there's a lot of capital flowing into that, into solar, obviously, and so who knows? I mean, that could be an innovation that really, you know, happens and makes the change that we need to have happen for Windows to be become a more common retrofit. So.
Actually, one small niche application which is on the market now, if I've got a motorized shade or an electrochromic window, both of which need power, and I'm doing it as a retrofit,
Sure.
and I don't want to run power lines up to the roof, I could put a little PV system there, maybe with a battery. Those products exist today. You can buy roof windows and skylights with little built-in PV, so you don't have to wire them up. So there are some specialty applications where it makes sense now.
You mentioned shades, but you know, thin film solar could be a shade, and that could become part of the shading process in a building.
Right.
So.
You know, sort of as a postscript, Steve, to what you're doing, a couple of weeks ago I was in the conference room in Department of Energy, which is the conference room for the Assistant Secretary for Solar and for Renewables and Energy Efficiency, and they just installed your technologies there, and they were still trying to figure out how it worked, and were surprised when the lights went on and or it got lighter or darker depending on some of the technologies. It was still, not only was the technology still learning how to work, but so were the occupants. But at least you're going to get the Assistant Secretary's attention
Right.
when she gets there.
Well, let me comment on that because we've been heavily involved in doing that. I'll just say an unnamed friend at DOE said to me, after struggling with this for months with the facilities people and the 100 different issues and problems and integration between 4 firms and so on, he said, I thought this was ready for the market. This has been an enormous nightmare, and I just smiled and said, that's why we need to keep working on this, because the pieces and parts are all fine, making it work as a system. And then the other little trick, which you're alluding to, just to let people know, is the dimmable lighting system, which we put in, seems to work fine. The windows do work fine, but the windows take 15 minutes to switch. So again, human factors. You walk up to the window, it's all automated, but you walk into the room and you want to darken the room, so you push the button. Nothing happens. Is that because it's broken, it's not working well? We've been working for the last 2 weeks on signs, and the signs say, you have to wait 15 minutes, don't push the switch twice. So anyway, those little things, if you don't get them right, can make or break technologies.
Yeah.
Thank you very much, John and Steve. Now we're going to have a short wrapping up by Professor Andrew Hargadon.
First off, I want to extend my thank you to the participants who spoke today, and just tell them what a privilege it was to hear their histories. This is a great opportunity for us to hear, by the original objective of the program, the roots of energy efficiency, and all that these guys and the others they've worked with have done over the past 30 years to create the world in which we're now sort of working. I want to thank also Chevron and their sponsorship. It's absolutely vital to, obviously, to these kinds of programs. And I do, echoing Dan, want to thank the staff and the Energy Efficiency Center in general who worked to put this all together. So thank you very much for all that. A quick introduction. I'm Andrew Hargadon, professor at the Graduate School of Management at UC Davis. I was part of the original team that put the Energy Efficiency Center together, and I served as its founding director. My research involves innovation, particularly science and technology-based innovation, and I find the challenges of energy efficiency to be sort of everything that innovation is, only more so in terms of its complexity. And so it's a wonderful thing to be working in this area, in this community. The Roots of Energy, the Roots of Energy Efficiency program, I want to just stress quickly, is both a celebration and a challenge. It's, at the same time pointing out how far we've come and also talking about how far we need to go. And I think the comments of the last panel were, in fact, quite nice in that regard. Santayana once told us, those who can't remember history are doomed to repeat it. And to that, I would add that actually history cuts both ways. It empowers us to sort of build on and stand on literally the institutions, the foundations of a lot of the work, for example, that you saw here today has put before us. It enables us to act in that world and to innovate on that world, and it's very nice in that way. But at the same time, and I want to point this out strongly, history also constrains us in the same, and in fact in the very same way. It gives us a particular set of institutions, set of habits and routines, set of behaviors and rules, and transactions and relationships that keep us very much locked into the same behaviors of the past. And it's in that spirit that I think we should be looking at, as we look at the roots of energy efficiency in California, that we need to pay a lot of very careful attention to the balance between celebrating what we've done and imagining what has yet to be done. So to that extent, what I want to talk about right now in my closing comments is this balance between holding on to the best parts of the past and really fighting to change those pieces of it that are still holding us back. I think, as the speaker showed, and obviously as you saw, and as President Obama spoke of earlier this week, California is clearly the leader in energy efficiency. And you've heard how today, through building codes, appliance standards, utility programs, new technologies, and very strong state leadership. These are all tools that were developed in California, proved out in California, and then have spread across the country. To that point, when Ralph Cavanagh says we're entering a golden age of energy efficiency, we can see all of the work that went before it, but we also need to then ask, so what will that golden age look like? What will the next 100 years, and in fact, if you study technological history, you know that in fact there are moments around sort of 2-3 decades where the next century's worth of institutions and habits are really formed. And all of the institutions of the last century, electronics, internal combustion engines, were set between roughly 1870 and 1900. And after that, it was really just a playing off of those original advances. And I think, as Ralph said, we're entering a golden age of energy efficiency, so what does that mean? What are we looking forward to, and what can we do next to make sure that the next 100 years is in fact building on a new foundation? Obviously, we want to use the old tools that have been developed in California, and obviously they still have much to do and much impact to have. Building codes will continue to be improved and I think, as importantly, exported across the country. Appliance standards continue to be approved and as well applied to new appliances and devices. Utility programs will obviously continue to be optimized and exported across the country. New technologies will continue to sort of be developed in our labs, national labs and university labs, and continue to be used to enable and drive new standards and new code. And then the leadership, the state leadership. As you saw, and in fact, as the Obama administration has done, the leadership that was developed in California is in fact being exported, to the rest of the country and internationally. That's all good, but that's also building on the past. And so what I want to challenge everyone to look at and to try and imagine is the wholly new set of tools that will fundamentally change the way we change energy consumption. And what I sort of feel by that is that the golden age of energy efficiency really brings us a golden opportunity that is really right now to create the new foundations for what's going to happen in the next century. We've made great progress, and I think one of the themes throughout a number of these speakers today is the progress we've made in moving from individual components, technical components like the refrigerator or like the light bulb, to systems like HVAC, daylighting, and moving up the stack, sort of the proverbial stack, from individual components to elements to systems. And I think our next step as we move forward is to think about the ecosystems, the actual business systems, the markets and the industries, and the ways in which the changes we make now act on those. If you ask me, obviously, if I'm going to make this challenge, I'm going to offer a few suggestions. How can we revolutionize the ways in which we make change happen? I think it's in revolutionizing the ways in which state governments, federal governments, utilities, other manufacturers, established companies like Chevron and others, startups, investors, researchers, and consumers work together. I don't think we've even begun to scratch the surface of the opportunities we have in building better relationships between those, to work together to create new solutions, new standards, and as importantly, new leaders for the next generation. Many of the accomplishments we heard about today were done in a system, in an era, literally, of conflicting worldviews, conflicting incentives, competing markets. It took decades, in many cases, to accomplish what they sat here and told us they accomplished. I don't begrudge them the effort, the persistence in making that happen. But I do say that if we're going to look forward to a golden age, one of the things of that golden age needs to be getting rid of the difficulties that these people went through in order to make these changes happen. So to that end, I just have a few quick points to make. One, we need to create a system for change that is faster, better, and cheaper. Steve, I love the points you had on your slide. I echo at least the alliteration. Faster, better, cheaper. We have to develop ways to quickly build and test new alternatives, whether that's new standards, new codes, new programs, new technologies. We have to find better ways to make and design our solutions, and particularly to make better solutions that are profitable for all of the parties involved. With John here from Chevron Energy Solutions and Steve with the National Labs, what is it that will make a solution profitable not only for the manufacturer, but for the company who has to install it, for the researcher who has to develop more of it, for the government, for society? We need to find ways in which those solutions provide even more profit for everybody who touches them. Today, again, what we've really seen in the last 30 years is a triumph of one set of interests over another. And what we really need to be working towards is a way in which those interests are aligned. And then lastly, cheaper. We need to reduce the transaction costs associated with coming up with a solution. That means, in fact, the time and effort it takes to create new standards, new building codes, makes it very difficult to put in place any building codes, let alone any new solutions. And all three of those together, faster, better, cheaper, really play out in the sense that if we can't do anything without enormous expense, a great deal of time, and only come up with a solution that benefits a few rather than a lot, it's going to be very difficult for us to try 2 or 3 or 4 times to get it right. And in complex systems like that, we need to be able to try more than one time to get things right. So what do I mean by that? How do we do those things? I think some of the really interesting comments that came out today were there, what David Goldstein talked about with standards, and particularly how standards and technology advancements need to work together. You need technical feasibility, economic feasibility to prove that a standard is justifiable and you can implement it. But at the same time, it's the awareness that a standard is coming that often drives the kind of investment in technology that is, in fact, its very justification. Michael Siminovich's work with the CLTC is an absolutely wonderful way of speeding up the process by working with manufacturers and policymakers at the same time to objectively vet new technologies and help see that they get into codes. The program at West Village here at UC Davis that the Energy Efficiency Center worked with, and the network of suppliers that they brought together to help the designers at the university, the planners at the university think about what alternatives were available at the stage at which they could actually put them into the project. And then, of course, Chevron Energy Solutions' key role in helping us to think through all of those opportunities. These are all examples of ways in which, if we think about making change better, we can start to think about how do we structure the relationships. At the Cooling Center, for example, there's a great solution that came up around evaporative cooling in rooftop units. And one of the things I think I'm most proud of in that center was their ability, working with Walmart, to go from an idea, concept, to a pilot program within 5 months, where we had in West Sacramento Walmart examples, prototypes of our technology sitting on the roof and actually running through tests. And I'll speak a little bit in a second about why that's so critical and also why that's so difficult. But I think, my hat's off to Steve Selkowitz for the mock-up, getting the architect, whoever it was who spent the money to build a 5,000 square foot mock-up, just to bring everybody together, and then afterwards to bring all of those other architects and engineers to see the solution before it had been implemented and improve on it. Aside from faster, better, cheaper, we also need to make the process more integrated. And what I mean by that is it's wonderful to develop a concept in a laboratory or in an institution. It's even better to get it out and put in place within a single territory in a building. But it's almost impossible to move from that utility territory to other utility territories, from that state and its regulatory system and set of incentives and codes to other states. The system, the energy, obviously the energy infrastructure is so fragmented today that in fact it's very difficult to make a change and not have to go ahead and reinvent it almost all over again to make it fit the next state or the next territory or the next owner-occupant or the next owner and occupant. And I think one of the biggest challenges we have is to try and figure out a way to make the market itself more integrated so that solutions that are developed can move more quickly across them. I think, in talking to John earlier, the sheer number of permits required to make a change happen in a single state is simply a transaction cost that needs to be paid again every time you move to another location, another state, or another project. And those are challenges that I think are the biggest challenges we need to work on as we move forward. Because without them, if you imagine a world without those challenges, you imagine a world in which, in fact, we can develop new solutions and try them out very quickly. Keep the ones that are good and jettison the ones that don't work. Lastly, we need to be open. I think that some of the hallmarks, aside from this fragmented nature of the energy sort of sector, one of the other hallmarks is its closed nature. It's a 150-year-old industry, and people who have an idea but come from the outside find it almost impossible to knock on the right door, and they can spend years as an entrepreneur or an innovator or even a researcher trying to find the right office with the right person at the right time of day that they will get the information they need to move forward or get the connections or get the introductions to move forward. And I think one of the things we need to be able to do to keep this golden age moving forward is make sure that all of the ideas that are out there, all of the improvements that can be made are made in an open system where there's access. What I think is one of the most valuable things that the Energy Efficiency Center has been able to do is look at technologies, immediately send them to the Lighting Technology Center, the Cooling Center, make sure they are in fact viable technologies, but then have a meeting in which the entrepreneurs and their potential investors can sit down at the table with emerging technology managers from the 3 utilities in the state, the 3 major utilities, IOUs, and say, if this works, is this something you would subsidize? Is this something you would pilot? Is this something you would support and roll out? And within a single afternoon, within a single 2-hour meeting, that entrepreneur and the investor who's considering that technology can get more access and more feedback than they might otherwise have gotten in 2 years of trying to go around and get that to work. So I think these are all the elements, faster, better, cheaper, integrated, and more open, that looking forward could fundamentally change the way we change. I do not want to begrudge. I mean, I look at what these people went through for the last 30 years and the amount of effort they put into making the state the leader that it is. And I both marvel at what they got accomplished and marvel at the obstacles that were in their way. And if we want to look forward to a new golden age, I think some of the biggest things we can do is start to rail against those obstacles. Now that we see how change happens and what it takes to make change happen, let's fix that as much as bring new solutions to the table. So with that, I want to thank everybody for coming today. I appreciate all of your time and attention. I appreciate all the speakers and what they gave us. And I wish everybody good luck in moving forward. Thank you.
Again, thank you again for participating in the Roots of Energy Efficiency. I hope you gained some new perspectives on the right turns, the left turns, the wrong turns, and the right turns that we have experienced and will experience in the next 20 years, maybe 50 years on energy efficiency. So thank you again for coming, and I hope you will come to Roots 3. Thank you very much.